As nations around the globe embark on the journey to rebuild their economies and infrastructures in a more sustainable and eco-friendly manner, the focus on low or zero carbon aviation has never been more critical. The aviation industry, a sector traditionally reliant on kerosene and other fossil fuels, is now at the forefront of exploring alternative energy sources to mitigate its environmental impact. Among these alternatives, hydrogen has emerged as a promising solution, offering a pathway toward truly sustainable air transport. For years, the aviation industry has been experimenting with hydrogen as a potential substitute for kerosene, seeking to replace the fossil fuel that has powered aircraft since the dawn of commercial aviation. The stakes have been raised considerably with Airbus's recent announcement that they aim to have commercial hydrogen-powered planes operational by 2035. This ambitious target, if achieved, could revolutionize the aviation industry, setting a new standard for sustainability in air travel. But is this goal realistic? To answer this question, we must first understand the environmental impact of current aviation practices. According to emissions research by the European Commission's Clean Sky Initiative, modern aircraft engines emit slightly more than 3 kilograms of carbon dioxide for every kilogram of fuel burned during a flight. Beyond carbon dioxide, these engines release soot, nitrogen oxides, and water vapor at high altitudes, all of which contribute to atmospheric warming. The problem is exacerbated by the formation of contrails and cirrus clouds, which trap heat in the Earth's atmosphere, further amplifying the warming effect. Recent scientific studies suggest that non-carbon dioxide emissions from kerosene-powered aircraft could have an overall impact 2 to 4 times greater than carbon dioxide emissions alone. This means that aviation is responsible for approximately 3 to 7% of the total global carbon dioxide equivalent emissions from human activities, translating to between 2 and 4 billion tons of carbon dioxide annually. The switch to synthetic fuels, while a step in the right direction, does not eliminate the nitrogen oxide emissions inherent to jet engines. However, initial research on hydrogen-powered combustion aircraft indicates a reduction in these emissions by up to 80% without significant efficiency losses. If hydrogen-powered fuel cells are used, the benefits become even more pronounced. Fuel cells eliminate nitrogen oxide emissions entirely, offering a clean and efficient alternative to traditional jet engines. However, hydrogen combustion and hydrogen fuel cells do emit water vapor, about 2.5 times more than synthetic fuels or kerosene. While water vapor is the dominant greenhouse gas in the atmosphere, individual water molecules are significantly less harmful than carbon dioxide molecules. Moreover, early simulations of hydrogen combustion show that the contrails produced by hydrogen-powered aircraft contain heavier ice crystals, which fall back to Earth more quickly, reducing the overall warming effect. Additionally, these contrails are free of soot, making them more transparent and less impactful on atmospheric warming. The result is a 30 to 50% reduction in the impact of contrails and cirrus clouds compared to kerosene-powered aircraft. In the case of fuel cells, the water vapor can even be captured and managed within the aircraft, further minimizing environmental impact. The differences in emissions are particularly relevant during the critical phases of takeoff and landing. Synthetic hydrocarbon fuels, while producing fewer particles than kerosene, do not significantly reduce other pollutants. Hydrogen, on the other hand, not only drastically reduces nitrogen oxide emissions, but also releases far fewer harmful particles and volatile organic compounds without any methane emissions. At this juncture, it is important to acknowledge the role of lithium-ion batteries in aviation. While they produce no local pollution or atmospheric warming, their current limitations make them more suitable for short-haul flights under 1,000 miles. This is significant because 80% of pre-COVID aviation industry emissions came from long-haul flights. Studies by the European Union suggest that if the aviation industry were ranked as a country, it would be among the top 10 global greenhouse gas emitters. Given these challenges, hydrogen has emerged as the preferred fuel for future aircraft development among major industry players. It offers a remarkable energy density, 3 times that of kerosene on a pound-for-pound basis. However, it also requires significantly larger storage volumes, necessitating innovative aircraft designs to accommodate these larger fuel tanks. This fundamental shift in design will influence everything from aerodynamics to passenger capacity. Before delving further into the application of hydrogen in aviation, it is essential to understand how it is produced. Hydrogen can be generated through various methods, broadly categorized into production from renewable resources, nuclear energy, and fossil fuels. Currently, the most common method is natural gas steam reforming, which accounts for about 97% of global hydrogen production due to its economic efficiency. However, this method still relies on fossil fuels and contributes to greenhouse gas emissions. Alternatively, hydrogen can be produced through the electrolysis of water, a process that can be powered by renewable energy sources like wind or solar. This method offers significant environmental benefits, particularly if the efficiency and cost of production can be improved. As we consider these methods of hydrogen production, the next significant challenge lies in how to store and integrate hydrogen effectively within aircraft structures, which requires innovative tank configurations and shapes. The storage of hydrogen on aircraft poses significant engineering challenges due to its low density and the need for cryogenic temperatures to maintain it in a liquid state. Liquid hydrogen has a volumetric energy density much lower than kerosene, meaning that tanks must be significantly larger to store the same amount of energy. This necessitates innovative tank configurations and shapes to integrate liquid hydrogen storage effectively into the aircraft design. Two primary tank configurations are considered: non-integral tanks and integral tanks. Non-integral tanks are mounted externally on the aircraft, such as on the fuselage or wings, which can lead to aerodynamic drag, but offers greater flexibility in design. Integral tanks, on the other hand, are built into the aircraft structure, offering reduced drag, but requiring the tanks to bear structural loads. The shape of these tanks is typically cylindrical or spherical, as these shapes minimize surface area relative to volume, reducing heat transfer and thus boil off. However, cylindrical tanks with end caps are often preferred for their ease of integration into the fuselage and higher volumetric efficiency. Beyond the shape and configuration, another crucial aspect to consider is how these tanks are insulated to maintain the hydrogen at cryogenic temperatures, which brings us to the importance of tank insulation and volume management. Insulation is critical for maintaining hydrogen at cryogenic temperatures during flight. Several insulation methods are used to minimize boil-off and maintain hydrogen in its liquid state. These methods include both internal and external insulation approaches, each with its own advantages and challenges. Internal insulation involves insulating the inside of the tank, directly shielding the liquid hydrogen from heat ingress. However, this method can lead to hydrogen diffusion into the tank wall, which increases thermal conductivity and reduces effectiveness over time. External insulation, where the insulation is applied on the outside of the tank, is easier to apply and maintain, but is more prone to mechanical damage and requires structural support to accommodate the expansion and contraction of the tank during operation. The choice of insulation materials is fundamental to the performance of hydrogen storage tanks, particularly in maintaining cryogenic temperatures and minimizing boil-off. Among the most effective materials and techniques used are multilayer insulation, vacuum insulation, and foam insulation. Multilayer insulation consists of multiple layers of reflective materials, typically alternating between metallized films and thin spacers, which are designed to minimize radiative heat transfer. The primary function of MLI is to reduce the amount of heat that penetrates the storage tank, thereby significantly minimizing the boil-off rate of liquid hydrogen. The performance of MLI is largely dependent on the number of layers and the quality of the vacuum between them. Each layer reflects a portion of the radiative heat back towards its source, creating a thermal barrier that substantially slows down the warming of the hydrogen. In practice, MLI can reduce heat transfer by more than 90%, making it an indispensable component in the design of cryogenic tanks used for hydrogen storage in aircraft. However, MLI is not without its challenges. Its performance can be adversely affected by factors such as layer compression during manufacturing and the presence of residual gases in the vacuum space. Compression of the layers increases thermal conductivity, which can degrade the insulation's effectiveness. Additionally, maintaining a high-quality vacuum is crucial for MLI to function optimally. Despite these potential issues, MLI remains the preferred insulation method for cryogenic applications due to its ability to provide excellent thermal performance with relatively low weight. Vacuum insulation is another advanced technique used to minimize heat transfer into liquid hydrogen storage tanks. In a vacuum-insulated tank, the space between the inner tank containing the hydrogen and the outer shell is evacuated to create a near-perfect vacuum. A vacuum lacking matter to conduct or convect heat serves as an exceptional insulator, drastically reducing the amount of heat that can penetrate the tank. Vacuum insulation is particularly effective when combined with MLI, as it further diminishes all three modes of heat transfer: conduction, convection, and radiation. The outer shell of a vacuum-insulated tank is typically designed to withstand external atmospheric pressure while maintaining the vacuum inside. This requires robust construction, often with additional structural supports to prevent the inner tank from collapsing under the external pressure. One of the main challenges associated with vacuum insulation is the long-term maintenance of the vacuum. Any breach or slow leak can significantly degrade the insulation's performance. To mitigate this, tanks are often equipped with vacuum pumps and monitoring systems to ensure the vacuum remains intact. Despite the complexity and higher cost associated with vacuum insulation, its ability to provide superior thermal protection makes it an indispensable technology for hydrogen storage in aviation. Foam insulation offers a lightweight and cost-effective alternative to more complex insulation methods like MLI and vacuum insulation. Foam insulation typically involves applying a rigid, low-density foam material around the inner tank wall. This foam acts as a thermal barrier, reducing the rate of heat transfer and helping to maintain the hydrogen in its liquid state. One of the key advantages of foam insulation is its simplicity and ease of application. Unlike MLI, which requires precise layering and careful vacuum maintenance, foam insulation can be applied more straightforwardly and is less susceptible to mechanical damage. Furthermore, foam insulation is more resistant to catastrophic failure. In the event of damage, the insulation's integrity is less likely to be compromised compared to a vacuum-insulated structure. However, foam insulation does have its limitations, particularly in its thermal performance. While effective at reducing heat transfer, foam insulation is generally less efficient than MLI or vacuum insulation, especially under the extreme cryogenic conditions required for liquid hydrogen. Additionally, the thickness of the foam directly impacts the overall weight and volume of the tank, which must be carefully balanced in aircraft design. Despite these trade-offs, foam insulation remains an attractive option for specific applications where simplicity, cost, and weight are critical considerations. The transition to hydrogen-powered aircraft engines introduces unique challenges, particularly in the realm of combustion. Hydrogen, while a clean and efficient fuel, presents specific difficulties due to its high flame speed and wide flammability range. These characteristics make hydrogen more prone to a phenomenon known as flashback, where the flame travels back into the fuel supply line, potentially causing an explosion. To mitigate this risk and ensure safe, efficient combustion, advanced systems such as lean direct injection and micro-mix combustion are being developed and refined. Both methods are designed to optimize the combustion of hydrogen in aircraft engines by promoting thorough mixing of fuel and air, thereby reducing the risk of hotspots that lead to the formation of nitrogen oxides, which are a significant concern in high-temperature combustion processes. Lean direct injection is a cutting-edge combustion technology that aims to achieve efficient combustion of hydrogen while minimizing harmful emissions, particularly NOx. The core principle of LDI is the injection of hydrogen directly into the combustion chamber in a lean mixture, meaning that the ratio of air to fuel is higher than in traditional stoichiometric combustion. This leaner mixture burns at a lower temperature, which is crucial for reducing NOx emissions, a primary environmental concern associated with high-temperature combustion. The effectiveness of LDI lies in its ability to ensure rapid and thorough mixing of hydrogen and air before combustion occurs. This is essential because hydrogen's high flame speed and wide flammability range make it prone to flashback, where the flame could potentially travel back into the fuel supply line. To prevent this, LDI injectors are meticulously engineered to promote complete mixing of the fuel and air, ensuring that the flame front remains stable within the combustion chamber. By controlling the combustion process in this way, LDI systems can maintain a stable and efficient burn even at lean equivalence ratios, where the fuel-to-air mixture is more diluted. A significant challenge in the implementation of LDI is managing the pressure and temperature within the combustion chamber to avoid hotspots that could exacerbate NOx production. Advanced injector designs, such as those developed by NASA, address this issue by incorporating multiple small injectors that distribute the fuel evenly throughout the chamber. This approach reduces the likelihood of hotspots and ensures a uniform temperature profile across the combustion zone. Additionally, these designs include features that prevent auto-ignition and flashback, making LDI a highly promising technology for hydrogen-powered aviation. Micro-mix combustion represents another innovative approach to hydrogen combustion in aircraft engines. Unlike conventional combustion chambers, which typically feature a single large flame, micro-mix combustion utilizes numerous small, localized flames. The concept behind micro-mix combustion is to increase the number of flamelets within the combustion chamber, thereby enhancing the mixing of fuel and air at a microscopic level. This results in a more homogeneous combustion process, which significantly reduces the formation of high-temperature zones that contribute to NOx emissions. In a micro-mix combustor, hydrogen is injected through a multitude of small nozzles, each generating a mini flame. This high level of dispersion and mixing allows for a more controlled and stable combustion process, even under varying engine loads and operational conditions. The micro-mix approach minimizes the risk of localized high temperatures, which are the primary cause of NOx formation. Additionally, micro-mix combustion systems can be finely tuned to adjust flame temperature and distribution, making them highly adaptable to different engine designs and performance requirements. Micro-mix combustion systems have demonstrated significant reductions in NOx emissions compared to traditional combustion methods. This is particularly important for meeting stringent environmental regulations and advancing the sustainability goals set by the aviation industry. The ability of micro-mix combustors to operate efficiently at low equivalence ratios where the fuel-to-air mixture is leaner than in conventional systems makes them an attractive option for the future of hydrogen-powered aircraft. As we look towards the future of hydrogen-powered aviation, addressing safety concerns is of utmost importance. Hydrogen, while non-toxic, is highly flammable, and its storage and use in aircraft require meticulous attention to safety protocols. The development of hydrogen-powered aircraft hinges on ensuring that these safety concerns are thoroughly addressed and mitigated. Hydrogen's flammability is a key risk factor, but when handled properly, it can actually be safer than conventional fuels such as kerosene or methane gas. One of the reasons for this is hydrogen's low molecular weight, which causes it to disperse rapidly into the atmosphere in the event of a leak. This rapid dispersion reduces the risk of fire significantly compared to heavier fuels like kerosene, which can pool on the ground and ignite, leading to extensive fires that are difficult to control. In controlled environments, hydrogen fires tend to cause less widespread damage because they burn quickly and upward away from people and structures rather than spreading across surfaces. Despite these inherent safety benefits, rigorous safety standards are essential in the development of hydrogen-powered aircraft. No commercial hydrogen-powered aircraft will be permitted to operate until it has successfully passed the stringent safety tests mandated by aviation industry regulations. These tests ensure that all potential risks associated with hydrogen use, including leaks, fires, and structural integrity under various conditions, are fully understood and mitigated. To further enhance safety, several measures are being integrated into the design and operation of hydrogen-powered aircraft. One crucial safety measure is the use of purging systems that remove air from fuel lines before hydrogen is introduced. This step is vital in preventing the risk of flashback during startup, where residual air could ignite prematurely. By ensuring that the fuel lines are completely purged of air, the risk of unintended ignition is significantly reduced. In addition to purging systems, the placement of fuel tanks within the aircraft is also a critical consideration. One proposed safety enhancement is positioning the hydrogen fuel tanks above the passenger cabin. This configuration offers additional protection for passengers, as it places the tanks in a location less vulnerable to impact and potential fire hazards. Should a fire occur, the design ensures that the flames are directed away from the passenger cabin, providing an added layer of safety. In the event of a hydrogen fire, the most effective strategy is to stop the flow of gas, which allows the fire to burn out safely on its own. This approach leverages hydrogen's rapid dispersion and the fact that it burns without producing harmful smoke, unlike kerosene fires, which generate toxic fumes and spread across large areas. Emergency response plans for hydrogen fires also recommend the use of dry powder extinguishers, which are effective in smothering flames. However, these extinguishers should be used with caution to prevent reignition, as hydrogen can reignite if any residual gas remains in the environment. Ultimately, the development of hydrogen-powered aircraft will continue to prioritize safety as the foremost concern. With the implementation of these comprehensive safety measures and the rigorous testing required by industry standards, hydrogen-powered aviation has the potential to be as safe, if not safer, than current kerosene-powered aircraft. This commitment to safety, combined with hydrogen's environmental benefits, makes it a promising alternative for the future of air travel. Major players in the industry, including Rolls-Royce, Boeing, and Airbus, are actively working to overcome these challenges. The general consensus until recently was that hydrogen-powered aircraft would not be commercially viable until at least 2050. However, Airbus's new target of 2035 has accelerated the timeline, bringing the possibility of zero-emission flight closer to reality. This optimistic forecast is supported by Airbus's Vice President for Zero-Emission Aircraft, Glenn Llewellyn, who stated, "We see it as something that airlines are asking for from us, and moreover, we see it as a moral obligation to enable climate-neutral flying for society." Llewellyn believes hydrogen is the most promising path to decarbonizing aviation, but stresses that widespread adoption of hydrogen will require collaboration across industries. This includes not only the aviation sector, but also energy providers, airports, regulators, and technology partners. The success of hydrogen-powered aviation will also depend on the continued decline in the cost of wind and solar energy, which are essential for producing green hydrogen through electrolysis. Hydrogen production costs are expected to drop significantly in the coming years as global production ramps up. Airbus's team has developed 3 prototype aircraft models, each designed to cater to different segments of the aviation market. These models are hybrid hydrogen aircraft, featuring modified gas turbines that burn hydrogen. Liquid hydrogen serves as the primary combustion fuel, while hydrogen fuel cells generate electrical power to supplement the gas turbines, creating an efficient hybrid propulsion system. For short-haul flights of up to 1,000 miles with around 100 passengers, Airbus has developed a propeller-driven system known as a turboprop. This system is highly efficient and climate-friendly, benefiting from hydrogen's lower emissions profile, particularly during takeoff and landing. The hydrogen fuel cell provides additional power, enhancing overall efficiency and reducing environmental impact. For longer-haul flights exceeding 2,000 miles, Airbus is developing 2 other options. The first is a more traditional turbofan design capable of carrying approximately 200 passengers. This aircraft will feature an extended fuselage to accommodate the larger hydrogen fuel tanks, with hybrid hydrogen systems powering jet engines on each wing. The second option is a revolutionary blended wing body design where the wings merge seamlessly with the main body of the aircraft. This innovative design allows for hydrogen fuel storage across the entire underside of the fuselage, offering a range of about 2,000 miles. The blended wing body also provides a wider cabin space, accommodating around 200 passengers. Airbus plans to invest hundreds of millions of euros in hydrogen technology by 2025, with further investments reaching several billion euros by 2035. Llewellyn emphasizes that Airbus cannot achieve this vision alone. We need regulators, airports, energy providers, and technology partners, and it's through collaboration with all these colleagues that this will truly become a reality. In conclusion, hydrogen-powered aircraft represent a critical step forward in the quest for sustainable aviation. While challenges remain, the potential benefits, reduced emissions, cleaner skies, and a sustainable future for air travel make this an endeavor worth pursuing. The journey toward hydrogen-powered aviation is not just about technological innovation. It's about redefining the future of air transport and ensuring that the skies remain open and clean for generations to come. If the aviation industry continues to follow this ambitious path, hydrogen-powered planes could not only shape the skies of today, but also lay the foundation for a more sustainable and environmentally friendly world tomorrow. It is up to us to embrace and support this transformation.